morning. Happy New Year. Yeah, 2026. Hope for a good 2026. Anyway, yeah, hope springs eternal. Anyway, I'm excited to be here. I'm excited to see many familiar faces here and some additional ones. It's great. Yeah, it's going to be, I think, going to be a fun semester. So let's just get started with some of the administrative aspects of the course. Everyone should ensure they have access. I'll email this URL to you, but it's also easy to find. It's also on the department's schedule, so you can see it and make sure you have access to it. Right. So the TAs for this course this semester are Ivan Gunther and Mohsen Raza. I'll be talking with them about setting up office hours as we had last semester. And I just booked the room for the problem session, so I'll just write here, TA, office hours, PDD, and the problem session we'll have as before, Fridays, 2 to 3, and they'll be in room 2540, because the classrooms are taken, the usual classrooms, okay? So I'll send an email with all of this, make sure everyone has that information. Right, so let's just talk about the general information again for the course. So there are, again, no required textbooks for the class. So, as always, there'll be lecture notes distributed, but I do encourage you to get access to additional resources. It's good to, everything shouldn't be filtered through the Deutsch filter. It's narrow band, and you need a broader band of information to learn this material well. These are some examples, but there's all kinds of stuff these days on what we call the World Wide Web, and you can find it. You can find it there, or something we used to call the library. Right? Very good. Okay, so the grading for this course this semester will be based on problem sets and a final project. Okay. The problem sets differently this semester will be every other week rather than every week. They'll be a little bit longer each week, but there'll be problems that you will have more time to work on, okay? And so there'll be 5 to 6 assignments, and they will be distributed on Thursdays and due in 2 weeks. In the same way, I'll just set up a Dropbox and you can drop it into the Dropbox. All right, so a few things. Let's see. We're at an inflection point in life with the rise of artificial intelligence. It's interesting for me, it's like this has been the first few months where I'm actually using AI and I love it. It's awesome. I mean, it's really been great. It's helping me to, learn about, I want to understand this subject, what are the right resources, what are the right papers, summarize it for me, and I'm going to talk to my group about it, about how I think it totally, it's like when, I'm now old enough, I remember when there was no internet, and then there was an internet, and it took a while for people to, well, first of all, for the internet to get good enough to be useful, but then for people to use it in a way that was productive. And it's totally, enhanced. I mean, God, every time you used to have to go, to a thing called the library, if you wanted a reference, and you'd have to turn out this giant book, and then you'd break and you'd put it on this thing called the Xerox machine, and you'd press it down, and it would it was a pain in the tuchus, and it was horrible. And it took you forever, and if I went on a trip, I'd have to print out a jillion things and, take a sack of papers with me. So yeah, the internet enhanced, and the same thing is true. It will happen. AI is going to help us to learn better, be more productive, and I totally encourage it. But, at the same time, if you're not using it productively, if you're just using it to take a picture of the problem set and have, Gemini solve your homework, it's your loss. And just don't do it, okay? Just don't do it. I mean, I'm not saying don't use AI to help you learn things, but don't have it solve your homework for you. We're going to have to all try to figure this out. The future of education is a thing that we are discussing in the Department of Physics and Astronomy, but I'm sure it's being discussed throughout all educators, how we, as educators, and I'm kind of a dinosaur, and I'll be 60 in a few days. What do people need to know? So when I was in high school, we weren't allowed to use calculators. Calculators were not, they were just kind of becoming cheap enough for people to buy, but the math teacher's like, no, you have to be able, you have this horrible thing with powers and square roots, and you had to take the logarithm and look at log tables. I mean, you did basically a slide rule by hand. I mean, do we need to know that? No. So there are going to be things that AI does that we don't do anymore, and I think that's okay. It frees your mind up for other things. So anyway, this is a discussion, it's going to be a discussion with you guys, and I want to hear from you in terms of how you, how it's productive for you, questions you have, how we can do our jobs as faculty to help you to learn best. And so my ears are open, okay? All right, very good. The other thing about the assignments, we were pretty lax last semester in terms of the due dates and so forth. And, it was okay. I mean, you guys are busy, and many of you are in labs and research, and you have duties and whatnot. But be nice to the TAs. And if you want, we want to try to get it done on schedule so that they can do their job as well. But if you're not going to get it, eventually I just gave up and said I'm just going to just let you do whatever the hell you want. People just dropped the homework and whenever they felt like it, and everyone just did. Let's not do that. All right. All right. Very good. Okay. Yeah. So here is the proposed syllabus for this semester. So there's a lot of interesting topics. We're going to continue our discussion that we kind of ended last semester, talking about non-classical light and different aspects that we haven't talked about in the first semester, including squeeze states and the like. Another important topic that we'll just generally be expanding upon this semester that we started with last semester is the notions of non-classicality and the way in which we can make borders between what we call classical and non-classical, and that border actually isn't so sharp, and there may be hierarchies of different levels of non-classicality and how we quantify that and what that even means. We'll talk a lot about that throughout this semester. And the context of quantum optics will be, the place in which some of these hierarchies and these distinctions will come into the fore. And they will include things like so-called quasi-probability distributions, and an important subject that we've mentioned, but we haven't really talked about, and I'm sure many of you have studied in different contexts, entanglement, okay? So there are lots of secret sauces that we might say, that give quantum physics special powers beyond what classical physics are, and we'll talk about some of that and the different ways these different things are related to one another. Okay, and then the last half of the course basically will be about open quantum systems, okay? And we talked about this in the first semester in a kind of phenomenological way. That is to say, we talked about the ideas of decoherence and dissipation and the master equation when we talked about the optical block equations, and we had T1 times and T2 times, and we saw how pure states became mixed states, and the notions of loss of coherence, and in addition to dissipation and irreversibility. That will be a big topic. That'll be kind of the central topic, or at least one of the big central topics of the semester. And we're going to study that in a more systematic and first principles way. We'll want to derive, to the degree possible, the master equation rather than sort of putting in dissipation by hand. And that has intimate relations. It's a very important subject, both from the sort of practical sense of how do we study and model real physical systems, which are always open system, but it also has deep connections to the foundations of quantum mechanics and the measurement problem and the notion of how the classical world emerges from a fundamentally classical world. All of that is tied in to our understanding of open quantum systems. So that's going to be a cool part of the subject. And then one of the parts of this that we'll talk about is, as I say, there's this intimate relationship between open quantum systems theory and measurement theory. And that'll be some of the topics of the last part of the semester. And the final project that we'll do will be actually a numerics problem, whereby we'll try to understand these tools that we'll talk about towards the latter part of the semester in the theory of so-called quantum trajectories and unravelings of the master equation and sort of see it in action in a problem that will involve numerics as well as analytics. All right? Yes, sir.
So last semester, one of the most helpful things about the problem session was that we, discussed different approaches to the homework problems. So we're having half as much homework, but the same amount of problem sessions. Are we just going to do the first half of homework, second half of homework, or are we just going to use both problem sessions to discuss, I guess, whatever the students feel like they need to discuss?
Well, I think number one is yes. I mean, I want to hear what I want to make this as productive for you as possible, but my intention of it, so the homework, so we'll have the first assignment will be distributed on Thursday. It will be due in 2 weeks, the first week of February. So the way I'm expecting it to go is that in the first week, it'll be just me more explaining the problems to you, making sure that everything is clear, and as different approaches to solving it. and then we'll have another week, we'll have another problem session, which will be more me answering your questions. And for us, I've tried this, I'm stuck here, I don't know what to do, this is what I've done, or we need to, maybe people want to work on things together and I can come around more. So that's how I expect it will go. Yeah. All right, anybody have any other questions? All right, very good. Well, let's get started then.
Politics, yeah.
Yay. All right. So, right, quantum optics, yay. The way we are talking about quantum optics is study of quantum coherence. With and within electromagnetic fields, what we say, light. Okay? And what we've talked about in terms of what I'm saying when I say with and within, some of the things we talked about last semester is the way in which we use light, say laser fields, microwave fields, RF fields, to control quantum coherence in matter. So we talked about Rabi oscillations, we talked about Raman transitions, and ways in which we talked about electromagnetically induced transparency, ways in which light is manipulating matter and creating quantum coherence within matter. But in addition, when I'm saying within the field itself, so the way in which we talk about quantum coherence of the light itself is the central subject, really, of quantum optics, okay? And as we've discussed, so today I'm just going to review stuff, get our minds revisiting things we talked about. So quantum coherence, or maybe I should just say coherence, what we mean by coherence in this case is the capacity of a system to exhibit interference. Okay, and so what is interfering? So, we have two different notions of interference that we think about in physics. When we think about classical physics, what interferes are waves. And waves are excitations or vibrations of a classical field. It might be an elastic field on a rod, a field representing displacements on a taut string, or something as abstract as the electromagnetic field in the vacuum. But that's still a classical field. So when we talk about quantum optics, we're talking about waves, we're talking about electromagnetic waves that interfere. in quantum physics, what interferes are probability amplitudes. That's the thing that interferes. And what the probability amplitude is it determines the probability of measurement outcomes. And that's it. I mean, that's all that quantum mechanics does for us. Oh, that's not a lot. But it's the bottom line of what quantum mechanics is that it is a prescription by which a rational person should ascribe a probability to the outcome of measurements. And as scientists, that's our goal. Our goal is to try to predict to the best we can possibly predict what we're going to see when we measure things. That's the goal of science, is to make those predictions as best we can. There's only so good we can do. We can't make 100% predictions. That's kind of, we got to live with that. And understanding that is, we still grapple with what this means at a fundamental level. But we do have this prescription, okay? Now, we have this notion of the classical limit. There should be some sense. We know that classical physics works pretty darn well in lots of circumstances. We went for millennia, without thinking about quantum mechanics, and it was a good model for the natural world. And if that's the case, and if the world is fundamentally quantum, there should be some way that we can think about a quantum to classical transition, a way in which, in the same way, or close to the same way, that Newtonian physics is a good approximation to relativistic mechanics when we're traveling slow compared to the speed of light, there should be some way that this is an excellent approximation to the world. And we've started to study this. We're going to study this much more this semester. But there's, the sort of the other side of this, which is things that are non-classical. So those are the kinds of things whose outcomes cannot be described by a classical statistical theory. It's not that classical physics need be deterministic, right? We have classical statistical mechanics, we have classical thermodynamics, and we understand that from the point of view of, it's a complex world, we don't have access to all the information, so we have, we use our best guess based on the information we have, but the information's out there, it's just too hard to have it. But there are certain phenomena that don't fall under this class, and that's important. Understanding when a system cannot be described in a classical statistical theory is where we say this is fundamentally non-classical. Right. Okay, so when it comes to the electromagnetic waves in quantum optics, all of this comes, from the very beginning of what we call modern physics, which is now over 100 years old, which is wave-particle duality. Right? So what we know is that light has both particle and wave like properties. What we have from the quantum theory is that we have quanta of the electromagnetic field, which are the photons. And to say that the system has wave and particle-like properties is to say, well, we can think about what are the particle-like properties that we observe. We have this notion of indivisible unit of the field that can't be divided. It's corpuscular. And that energy is absorbed and emitted in photons. These corpuscular units, these individual units of the field, are the things that make up the empirical evidence that we have for at least one part of the individual, right? And that these individual units carry units of energy, momentum, angular momentum, spin, etc. Right? But to say that they have wave-like properties is to say that there is quantum interference. And as we described, the interference we can describe as maybe let me write this up a little higher. We have quantum interference of what we have called histories. That lead to measurement outcomes. So as we've discussed, the notion of a history is a different generalization of the notion of a path, right? We often think about, in classical inference, there are different paths and there's interference between the two paths. But we can have a more complicated set of paths or set of conditions that are possible histories of what could have happened that could lead to the measurement outcome that we see. And if there are multiple of these histories that can lead to those outcomes, then those histories will interfere with one another unless they're distinguishable. So really we should put in here indistinguishable. This is something I really want to emphasize because it's going to be foundational to how we lose interference is when the histories become distinguishable. And the ways in which histories can become distinguishable include the way in which the system that we're measuring interacts with a vast degree of freedoms that's called the environment. And if the environment can distinguish, if the environment contains a record, somehow, even if we don't have access to that record, but if the environment has a record as to which of these histories occurred, then we're back to classical statistics. At that point, those histories don't interfere. We just have a classical statistic probability. Maybe this happened, maybe we don't. And actually we can know which one happened because the information's out there in the environment for us to have access to, okay? Now, again, going back to this question of the classical limit versus the non-classical, we had different kinds of scenarios that we thought about. If we have photon counting, of one photon at a time, okay, then what we saw, and I'll review this again, is this is essentially classical. That is to say, any interference effect or any effect that we see in terms of this probability of seeing a certain photon is completely consistent with treating the electromagnetic field classically. Of course, we'll come back to this, if we're seeing these discrete photons, these individual corpuscular units, that is not part of the classical description. We put that instead into some aspect of the nature of the quantum nature of the matter. But we in no way ever need to think about the field itself as a quantum field. We have a completely consistent, self-consistent theory of what we observe treating the field classically, okay? And the non-classical, so the multiphoton interference, coincidence, or correlations, those can give us something that is truly non-classical. So one of the things we learned last semester is that one of the ways we can distinguish the non-classical from the classical is in terms of photon statistics. Right. Right. Okay. So let's just quickly review as we were talking about to say, if we think about this classical interference, in order for us to distinguish this from the quantum nature, our kind of hydrogen atom of thinking about wave interference is think about an interferometer. And we talked about the Mach-Zehnder interferometer as a nice picture where we have some incident field and some output field at some output ports that are associated with multiple paths, in this case, that the wave can travel, or equivalently, the photons can travel that can end up at my detector over here. And so we have our incident field at some, let's say the field at some incident position here at the beam splitter as a function of time. We have some output field at the output position as a function of time. And then we have the intensity in a square law detector. So, in the classical theory, we write the intensity is equal to the time average of the square of the field maybe with some constants out here. If we have this, that's the actual intensity. This is the time average. And when we do that time average, it's convenient to break up the field into its positive frequency component and its complex conjugate, which we call the negative frequency component. So this is the complex conjugate of the positive frequency component. The positive frequency component is thinking about the inverse Fourier transform of the system, but only over the positive real axis. Okay, and this is the negative frequency component. And when we do that, what we find is that this is equal to some constant, which I really don't care about, times E minus dotted into E plus okay. So that's the intensity of the field is given by kind of the square of this complex amplitude, okay, as we remember. So we'll forget about that constant, we'll just call this thing the intensity. Let's just say this is, its polarization. We'll forget about the vector nature of the field, and I'll just call it E minus dot times E plus. Right, so I'll just say that this thing is equal to some polarization, and just get rid of the polarization. I don't want to drag around the vector nature of the field. In the interferometer here, if this thing has a path length L1 and a path length L2, that gets me to the final, I missed my final beam splitter. Then this thing is a superposition. The superposition principle tells me that what I see here is the superposition of these guys, and with all the beam splitters that are 50-50 beam splitters and all the phases as we've done before, this is equal to R at the retarded time. So E at the input, where this is the time in the past that the light propagated, right? So we look at the superposition of the two fields that we see associated with the field at the retarded time earlier in time, this path and that path. And we have, this is the superposition principle. Right, and so what we then find is this output intensity, in this case, will be equal to 1/4 times the intensity, the input intensity coming from the first path at the retarded time, plus the intensity from the other path. And then what we have is twice the real part of E minus T1, E plus T minus T2, okay? And this then, we said, is a correlation function. And that correlation function is what leads to wave interference. So that the intensity that we see here is not just equal to necessarily the sums of the two intensities, but it is dependent on this interference term. Okay. Now, in the case that we have, let's say we have a monochromatic plane wave, so that the input field, the positive frequency component, has some amplitude e to the I k dot r e to the minus I omega t, then for that kind of monochromatic field, the output intensity we see at this port, each one of these guys is going to be the same. So this is going to be twice the input intensity, where the input intensity is going to be equal to quarter E naught E squared. So what I have is, and then a half of I in plus, factor out that 2 times a quarter, E naught squared over 2 times e to the minus I omega T2 minus T1, the real part. So this is the input intensity, and what we have is this is equal to the input intensity times a half 1 plus cosine omega T1 or T2 minus T1. Right? This is our interference that we see as a function of T1 minus T2 or T2 minus T1, which is L2 minus L1 over C. And what we see in this case is, we write this as omega times this, that the output intensity is equal to the input intensity if I have a balanced interferometer, but none of the intensity comes out this port when this phase is equal to a half a wavelength, right? And then I get a dark spot, and this I get this quantum interference that we're, of course, all familiar with, okay? Now, what was I going to say? Yeah. What we discussed a moment ago is that in classical physics, we need to allow for statistical fluctuations. So we may have the case that we don't have a field that has a deterministic electric field value as a function of time, but could have a statistically uncertain case. So for example, we talked about last semester the idea of collision broadening. So if I think about the radiation that is coming from a source where I have an oscillating dipole, but I have random collisions between them, I can think about the electric field as a function of time in that as something which in some reasonable model is something that oscillates for some time and then all of a sudden jumps. And I have a random phase. Where this jump happens is statistically, I don't have the information. It's coming from the fact that I have thermal fluctuations, and that fluctuation means that I don't have phase coherence for a infinite amount of time. There's a finite amount of time that the phase of oscillation here is correlated with what it was at an earlier time because it randomly jumps, right? And when if we have such a situation, we would say that I have some probability distribution. That's a functional of what the electric field amplitude. I have to decide from the statistics of the source, the way the source is, what probability I assign to a particular electric field. And under certain statistical properties that we discussed, if the system is ergodic, meaning that it explores all the possible amplitudes over time as if I sampled them at the same time from the same probability distribution, then my intensity, I can think about, instead of a time average, I can think about it as a statistical average. Okay, so this, we had over there that bar up top, I said time average. Now I'm saying this is equivalent to a statistical average. Right? And for the case of collision broadening, if I thought about for a single mode, let's say, at some particular position, I can think about a random complex amplitude. And as you may remember, if I have a collision broadened system, we can derive what that probability amplitude is. You guys remember what that, it's not a probability amplitude, the probability distribution of this. This is a classical statistical, right? So I have a phasor in a phase space. There's the real part and the imaginary part of this complex amplitude. And it's some random value. I don't know where it is on the phase plane. But I can assign a probability to it. You guys remember what that probability is? What's that? I said Gaussian. Excellent. So what we have is the probability of this alpha is if I have collision broadening with n oscillators, then this probability distribution was Gaussian in the complex plane, and 2D, as I already said, in terms of the real part and the imaginary part, okay? Right, and in this situation, when we looked at the Mach-Zehnder interferometer, so now I define, so I have this correlation function where did that correlation function go? Here it is. So before I had my time average, now I'm going to look at my statistical average here. So my output intensity in this case was equal to a half the input intensity plus the real part of what we call G1 of T2 minus T1. So G1 of tau was equal to the statistical average of E minus at tau, E plus at tau, at 0. The aspect of that had to do with, as you may remember, the fact that we had stationary statistics. That is to say, really we have T minus T1 and T minus T2. We had that two-time correlation function over here. However, if I have stationary statistics, all that matters is the time difference, not where I am in time, because the statistics are independent of the origin of time. Yeah.
So we're just saying that stationary statistics can be used when your like initial laser going in isn't changing.
Right. If the nature of the fluctuations are not changing with time. The statistics, the probability distribution is independent of time. Then we have stationary statistics, as we might have in natural light. So it's not necessarily a laser, but it's whatever the light is. Okay. And in this case, what we showed sort of last semester is that what this thing equals is the input intensity e to the minus I omega tau times e to the minus tau over tau c, where tau c is the correlation time. And in that case, what we find is that this input intensity, or the output intensity, I should say, as a function of this, look like this. The point being that when, again, this is equal to omega over c, L2 minus L1, okay? So there is a correlation time, or a correlation length, which determines the coherence that we see, and the reason that, and what this says is the following: if the path length difference is too big compared to the correlation time, then we don't see interference. In that case, half of the intensity comes out this port, and the other half comes out that. We have lost coherence. The way we have lost coherence is shown here. The phase here is not correlated with the phase here. And when we lose that strict phase coherence, we lose interference. Stabilizing our laser is critical to ensuring that we're going to have long phase coherence. We have a very narrow line width. Okay. Right. Very good. Okay. So the other thing we saw in terms of the statistics, when we think about classical statistical optics and this kind of probability distribution is, okay, so what we saw here is that the two-time correlation function of the electric field amplitude with itself has finite coherence. We also saw that we have intensity fluctuations. So if I looked at, even on a single detector, and I looked at the intensity that I see on this square law detector, it will fluctuate. If I were to look at the light, even put through a narrow band filter that had a pretty strongly monochromatic or close to monochromatic field, and I looked at the photocurrent that I see here, it would fluctuate because of this probability distribution, the one that we have over here. And so what we saw last semester is if I looked at, for collision broadened light with this probability distribution, that the expected value of the intensity to the nth power is n factorial times bigger than the intensity to that same power, right? And so that's a pretty huge amount of fluctuations. And moreover, if I just look specifically at the case of the variance, that's to say the mean squared fluctuation, right? So I squared is equal to 2 times I squared minus I squared is equal to I. That's just classical fluctuations. It's the fact that the electric field that's coming out of this light bulb, its amplitude is not just oscillating, but its amplitude itself is fluctuating.
Should that be an I squared?
It should, thanks, Nate, sorry. The square root of that is really what I was thinking is that. Thank you. All right. Good. So it's just a little bit of a reminder of what we had talked about in terms of just the classical fluctuations that we see, which we now want to compare in thinking about the quantum field. So now our positive frequency component becomes an operator. It's a quantum field. It's a operator that is a function of the points in space-time. That's what makes this a quantum field. And when we quantized the field, it was convenient for us to think about a modal decomposition. So we expanded this in a complete set of functions, orthogonal functions, that we call modes. What is a mode? It's a complicated story. We had the normal modes and we have cavities and so forth, but it's a little more complicated in general. I'll just say we had some way of expanding the field like a Fourier decomposition in, for example, in a cavity. We might have something like this where we have some modes, okay? When we go to the quantum field, what were the complex amplitudes became the creation and annihilation operators. Okay? So in this case, what we have is that the complex amplitudes become the annihilation operators. the annihilation operators for the quanta, the photons, right? And the Hilbert space is what we call the Fock space. The number operators, which count the photons in a particular mode, A dagger A, are the quantum analog of the intensity. So the intensity is now comes in these discrete packets, these discrete units, and the number of those units tells me how much intensity I have in the field, okay, or at least in this particular mode. And our Fock states have a basis, which are the Fock states, which have some number of photons in a given mode, okay? So that these are the eigenstates. If I have a particular mode with n photons in them, this is what we call a Fock state. I don't really like that term because basically any state in Fock space should be called a Fock state. And we can have states in Fock space, as we know, which are not eigenstates of the number operator. But that's just what people call them. They call Fock states number states. Yeah?
I had real trouble about that when I was writing the thesis. Okay, I call this Fock state. Why
I know, someone screwed that up and we're stuck with it. Yeah. Oh well. I prefer to call these number states, but they are also called Fock states. Okay? Right, so we have our quantized electromagnetic field with positive frequency components that are the quantized versions of what we had before. We have other things like all our quantities like the Hamiltonian, which is the quantized version of the energy in the field, and we write this in the mode decomposition. This was equal to the energy associated with a set of harmonic oscillators. And the momentum in the field told us that each of the quanta had a momentum of h bar times the wave vector, etc., etc. Okay, right. And the important set of states that come from the Glauber theory are the coherent states, the Glauber coherent states, which are quasi-classical states. The coherent state, I'll just talk about a single mode and not put the mode label on the moment, are eigenstates of the annihilation operator. They kind of unquantize and take the hat off of the annihilation operator and turn it back into an eigenvalue, right? And so the intensity, or equivalently the number of this, is the square of the amplitude, just as we have classically. Okay. But this is the mean number of photons. This state is not a number state. It has a fluctuation in number of photons. And what is that fluctuation for a coherent state? Yeah.
Square root of n.
Square root of the mean, right? And we remember that we can expand the coherent state in the basis of number states. What is that expansion?
Factorial times
No, e to the minus alpha squared.
Over 2.
Yeah.
This is actually,
Factorial
getting closer.
alpha n, yeah, alpha to the power of n. Not just alpha.
No, I'm sorry,
Alpha.
alpha to the n. So this, I'll call this C sub n, the probability of there being n photons in the mode then is the square of the amplitude, which is e to the minus alpha squared to the power n over n factorial, which is e to the minus which we remember is a Poisson distribution. Right? Good. We will remember, start to remember this more. And these fluctuations are Poisson counting noise associated with a Poisson stochastic process. So there's this, of course, the Poisson distribution, and then there's a Poisson process. And as we discussed, coming back to this question of the idea that we can explain in a semi-classical way what we observed in certain measurements. If we have a monochromatic field with a stable intensity, incident on a photon counter, what we see as a function of time, the photocurrent, at least for if we have a sufficiently low intensity and fast detector, is click, 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 and we have this random set of clicks in a Poisson process. Right? And empirically, what we see is that the probability, if I look at any time interval here, I could pick any 2 times and look at some time interval t and ask what's the probability that I see n photons or n photocounts. I'm going to say photons, n photoelectrons in that time interval, then it's equal to a Poisson distribution. Where the mean number of photons I see in a given time interval is given by, well, I have an intensity of the field times, say, the area, the cross-sectional area of this mode tells me the power, the amount of energy per unit time that's flowing through that area, divided by h bar omega. That's the mean number of photons that hit this thing, times some factor eta that we call the detector quantum efficiency. And this is derivable from semi-classical mechanics. meaning we treat the field classically, but the matter quantumly. And using Fermi's golden rule, we get this. The fact that this is a Poisson process is a further assumption that the photo or the quantum jumps are statistically independent. So this is not, seeing these photon counts is not a signature of the quantum electromagnetic field. Moreover, what we have, then what we can say, as we've discussed, is that we can call the quantum states of light that we say are equivalent to what we call classical light. In that those quantum states are completely consistent with this semi-classical model, are the coherent states and any statistical mixture thereof. So when we call the states, we said that they are a statistical mixture of coherent states. And this little bracket here, I'm just saying for it could be multi-mode. So this could be a set of what I'm saying here is this state is a coherent state for mode 1, a coherent state for mode 2, coherent state for mode K. That's what I mean when I'm writing those curly brackets here. Okay? So if I thought about a single mode, the mean photon number, or mean intensity in this case, would be equal to this. Just like we had when we thought about the classical statistical theory over here, where I think about writing this in terms, where did I write it? Where's the probability distribution? Anyway, these kind of statistical averages. It's exactly what we would get from the classical theory. If I have this kind of classical light, it has certain properties. So if I ask, for example, what is the fluctuation in the number of photons that I would see in this problem? That is the mean of n squared minus mean of n. Okay, so this we said is that average squared. This is equal to a dagger a times a dagger a. And we remember that when we want to take the expectation value of anything, so the trace, the expected value of some observable with this kind of state, let's say for a single mode, is equal to the expected value with respect to the coherent state averaged over that distribution. Everyone see that? So when we're doing expectation values where this is a coherent state, we remember that it's very convenient to put this, to commute this into normal order by putting all of the annihilation operators on the left and all the creation operators on the left, all the annihilation operators on the right. So this becomes a dagger squared, a squared, plus a dagger a. And so what we see over here is that the mean of n squared is equal to the integral of the expectation value of this normally ordered product plus the mean n. And this is alpha to the fourth. So this is equal to the statistical mean of alpha to the fourth plus the mean n. So when we put that together, what we see is that the fluctuations in n squared are equal to the mean n plus the fluctuation in the intensity. What I mean by this is the mean of alpha squared minus the mean of alpha squared. So I just want to conclude here by reminding us of the following thing, and we'll pick this up again next lecture, is one of the things we see about classical light is that the fluctuations that we see in the photon number are always bigger than the Poisson fluctuations. And that excess fluctuation is because the intensity is not fixed. Because we have a statistical mixture of coherent states, we have classical intensity fluctuations which always increase, which is to say that the fluctuations that we see here at this case were just due to the fact that we can think about that as Poisson fluctuations for a fixed intensity is kind of semi-classical. If we have classical light, we will always have excess noise. And so one of the properties we had of classical light is that it is super Poissonian, meaning that the fluctuations in this are always bigger than or equal to that. And if we see fluctuations that are less than Poisson, well, what that means is that we could not have written this. What I mean by this, if it's classical light, is that this is an honest-to-God probability distribution. If we have fluctuations in photon number that are less than this, then we could not have written the state as a statistical mixture. And so that's one example of a case where if my representation here, my P representation is not an honest-to-God probability distribution, then my state is not classical. We can have fluctuations that are reduced. And we already know that. What's an example of a quantum state whose fluctuation in photon number are less than that? Coherent state has exactly equal to that. A photon state, and a Fock state, a number state has no fluctuations. And if I try to write the number state, its density matrix in this way, which we'll do for homework, we'll find this thing is not that. It's a completely weird function which cannot be thought of as a statistical mixture. And that's an important resource, as we will see, both for things like quantum sensing, but also for quantum computing. So we'll tie this up next time. We'll remind ourselves a little bit more about the classical versus non-classical light features.